Hello, I'm Ahto Buldas. This lecture is about secure and efficient implementation of electronic money. And this work was done together with Dirk Praheim and Mert Saarevera. So a little bit of motivation. Central banks are discussing potential use of central bank digital currency, CBDC, and technical challenges are security and scalability. Blockchains provide high level of operator-independent security, which means that the operations can be, central banks can outsource the operation of payments to private sector while still having full control over the money. Money can be represented in various ways by accounts, bills, UTXOs, like in Bitcoin, for example. In this talk, we show that secure and scalable blockchain implementations depend on the choice of the representation of money, and secure and the scalable solutions are possible by using bill money scheme. The agenda of the talk. So we describe money schemes first and make categorization of payments depending on the money scheme. We talk about blockchain implementation of money schemes. Then we go to decomposability of the implementations of money schemes, which is the basics of scalable solutions. We go through security aspects of blockchain implementations. We look at the bill money scheme and its secure implementations, and then we go through client-side audit procedures and their security. And the client-side audit procedures are crucial for outsourcing securely the money scheme operations. Okay, so let's start from money schemes. Money itself can be represented as a set U of units of money, and a value function nu, which defines the value of every unit. We have ownership of units. It's a function beta, which assigns for each unit U its owner beta of U. If we have the set U of units, we know how valuable the units are, and we know by whom they are beared, or by who owns the units. We have so-called money distribution. Now, so far, we described the statics of the money scheme. Now, payments represent changes of ownership money, so that the total amount of money, which is computed like here, so we go through all the units and add up their values, and this value does not change. We don't look at the emission of money and redemption of money in this talk. And if B is certain bearer, we can also compute the money of B by just adding up the values of all units that B owns. And money scheme is a pair, M and P, where M is the set of all allowed money distributions, and P is the set of all allowed payments. What we require about all money schemes is so-called quasi-completeness. It's a natural property that for every money distribution M, there exists a composition of payments such that the final result of these payments, the final result as a money distribution, P has no money. So this means that if P has certain amount of money, he or she can spend all her money. Examples of money schemes: account scheme. Payments are called payments change values of two accounts, the payer account and payee account. and such that in the resulting money scheme, money distribution, no accounts are created or deleted, ownership of accounts stays the same, and total money stays the same. In the bill scheme, payment just changes the ownership of a unit. So no bills are created or deleted during payment. The nominal values of the bill stay the same, and the payment just changes the owner of a unit, a bill. In the UTXO scheme, which is in use in the Bitcoin scheme, payments delete a set of units, which are called UTXOs, and create a set of new units so that the total money stays the same. Okay, so payments have their complexities. If, say, M is the current money distribution and we have a payment P, we can characterize incompletely the payment by three subsets: U minus, U plus, and U zero. U minus is the set of all units that P deletes. U plus is the set of all units that P creates, and U zero is the set of all units. The payments, the payment changes the parameters of nu and beta of this payment. To completely characterize the payment, we of course have to say what the parameters of the newly created units are, and we also have to describe the way how P changes the parameters of some units. But for the complexity, we don't have to do it. We can define descriptional complexity as the number of all units that P somehow changes, either deletes, creates, or changes the parameters of. We also have input complexity, which is the sum of the number of units that are deleted and the number of units that the parameters are changed by P. For example, if you have a trivial payment which does nothing, its both complexities are just zero. Okay, so let's go through some more examples. Say we have a single bill transfer, it changes the bearer of a single unit U and does nothing else. In this case, both complexities, descriptional and input complexity, equal to 1. For account payments, which change the values N1 and N2 of two units U1 and U2, so that total money stays the same, the values of those two units are changed. In this case, both the descriptional complexity and the input complexity is equal to 2. For the UTXO payment that deletes K units and creates L units, the descriptional complexity is K plus L, and the input complexity is simply K. So every payment can be characterized or represented as composition of so-called composition irreducible payments. A payment P is composition irreducible if there exist no payments P1 and P2 with descriptional complexities lower than P, so that P is the composition of those two payments. And we have a full list of those composition irreducible payments, and they are the following. So zero creation is first, it creates a unit with value 0, does nothing else. In this case, descriptional complexity is 1 and input complexity is 0. We have zero deletion, it deletes a unit with value 0. Its descriptional complexity is 1 and input complexity is also 1. We have single unit transfer that changes the owner of a unit, as I already said. it's both complexities are equal to 1. We have transfer with recreation. It deletes a unit and creates a new unit with the same value. Input complexity is 1 and descriptional complexity is 2. We have 2 unit split. It creates a new unit and changes the parameters of a unit. So in this case, we have descriptional complexity 2 and input complexity 1. We have 2 unit swap, which, for example, account payment is a 2 unit swap. It changes the values and possible pairs of 2 units, and its both complexities are equal to 2. Also, finally, we have 2 unit join. It deletes a unit and changes the parameters of a unit, and it has similar complexities than 2 unit swap. Okay, so in this talk, we try to characterize money scheme implementations, and we are looking at implementation from formal perspective, and we look at the implementations by transition systems, implementations of money scheme by transition system. Transition system is a pair S and T, where S is the set of states and T is a set of state transitions, which are functions that change the state. We assume that it always contains identity transition that does nothing with the state. By an implementation, we say that implementation of a money scheme, we say that ST implements transition system, ST implements a money scheme MP if there is an interpretation map pi that for every state S of the machine, the transition system, we also call it the machine, it interprets the state as a money distribution. So if the machine is in the state S, we apply pi and know what the money distribution is. And for every payment and every state which is interpreted as a money distribution M, there is a transition T, so that if S prime is T of S, it is interpreted as a money distribution PM. So as if P was applied to M. So here you see in the picture, so we have the interpretation of pi here, and if there is a transition that transforms a state S to S prime, if we apply pi to both S and S prime, we will see here, it's like a commutative diagram here. We see that this change is interpreted as a payment P. Okay, for scalability, we have to use decomposition of a money scheme, and we define formally what the decomposition is. We have 2 transition systems, S1, T1, S2, and T2. We say that these 2 machines decompose a money scheme MP if there is an interpretation map pi, which is a function from the direct product of the state of those machines to the money scheme, so that to the money distributions, so that every pair of states is interpreted as a money distribution. And for every payment, you see here that if every payment is represented as a pair of transitions in those 2 machines, and so if we apply a payment P, we have to apply 2 transitions in both machines. And if you apply the interpretation map, we will see that these two changes into machines are interpreted as a payment P. Okay. So if we have a transition system, we call the evolution of the transition system. It is sequence of changes of state in the system. So we denote the evolution by E, and evolution is a sequence of pairs. So first we have initial state as 0. We have certain time indicator tau 0, and we have transitions that happen in the system together with timestamps. Say T1 tau 1 is a pair of transition and timestamp, etc. up to Tm and tau m. And the final state is just the composition of all those transitions applied to the initial state. And evolution describes the execution of the transaction system in time. For security critical systems, such as money schemes, it is also vital to store the evolution and protect the integrity of this evolution. And we use cryptographic certificates C0 up to CM for that. And so the certified evolution is described by triples, where at every event a certificate is added. These certificates can be verified by the verifiers of the evolution. And the cryptographic measures should guarantee that this evolution cannot be maliciously modified without making such modification evident, making it inconsistent, making the certified evolution inconsistent. Certificates do not verify anymore. What we also require, which is a crucial requirement, is that certificate must also convince verifiers that there exist no alternative versions of the evolutions of the evolution. So there is one and only true evolution of the system. For example, double spending is one of possible violations of such unique evolution. It's also important for the verifiers to see that what they observe and verify is the whole evolution. So this means that the next potential certified record has not yet been created or has not yet been added to the blockchain. And this suggests that certification should be done in batches or blocks, BI, by a determined time schedule. So by looking at current time, we know how many blocks there should be. And so, yeah, here the blocks actually represent compositions of transitions. Some blocks may be empty, and in this case, they represent the identity transition. And certified data structures in this form we can call blockchains. So they represent, every blockchain is basically such a data structure. Implementations of a blockchain. We have a transition system and we have a network of machines, which is one component of which is file repository, stores certified blocks, and on request provides applications with blockchain data. We have a certifier that regularly, based on the block, creates block certificate based on cryptographic hash the block. We have a transaction validator. It verifies transaction orders using the current state of the system, creates blocks, obtains certificates from the certifier, and stores certified blocks in the file repository. You see the schematic view of this. We have a file repository here. We have transaction validator here, and we have transition orders coming from an application. Transition validator has the state. It creates certified blocks, stores it to the file repository, and before doing that, it obtains a certificate from the certifier. For example, in Bitcoin, the certifier is so-called miner who creates proof of work for the blocks. For efficiency reasons, we need sometimes sharded blockchain implementation, which means that we have two machines, two transaction validators. There is a rule how to which transactions are processed by which machine, and these machines produce sub-blocks, corresponding sub-blocks, and they create sub-blockchains by using the same certifier. Here you see the blockchain of the first component, first transaction validator, and there you see the blockchain of the second validator. We need, in this case, we need some additional information pi that is additional information for verifying the contents of the block against the certificates. Usually they are in the form of hash chains. So if we want to decompose a money scheme, important notion is atomic decomposition. And if we want to represent or implement a money scheme as a sharded blockchain, we have to keep in mind the restrictions that blocks are produced on a fixed time schedule. And there is a limited time to decide whether to include certain transactions to the blocks or not. And we know a famous impossibility. It is called the atomic commit problem, also sometimes called two generals problem. There is no deterministic time. There are no deterministic time protocols that ensure that either both T1 and T2, the component transaction of a certain payment, that they are both included into the corresponding sub-blocks, or none of them is included there. And so it is always possible that instead of T1 and T2, we execute T1 and 1. So here we do nothing in the second component, or 1 and T2, which means that we do nothing in the first component. So it's not possible to exclude that instead of the full transaction, partial transaction is executed. And we can only ask how these partial transactions are interpreted in the money schemes. Are they payments? Are they partial payments, or what they are? And the atomicity requirement of such atomic decomposition means the following 4 requirements. So let M be a money distribution, which corresponds to two states S1 and S2. PM is the resulting money distribution if both T1 and T2 were applied. M1 is the money distribution resulted in the case where only T1 is applied, and M2 is the money distribution where only T2 is applied. So what we require is that those erroneous payments or partial payments. So we first require that they are payments. They are interpreted as payments. The second requirement is that if as a result of payment P, the money of a bearer B decreases. So in the resulting money distribution, B has less money than without applying this payment. Then the amount of B's owned value is decreased. It should be larger or equal than the amount of value, B's value decreased in the erroneous, in both erroneous cases. So this means that what those atomicity errors can do is it just B transfers a bit less of money than intended. And if, again, this is similar if somebody is paid to, so if B's money increases during the payment P, then in case of erroneous payments, it just can increase a bit less. And if the payment does not change the money owned by B, then also M1 and M2 should this in M1 and M2 nothing should be changed with me. So third parties money is not changed by those erroneous payments. Okay, so it can be shown that if S1, T1 represent money schemes MP1 and MP2, P1 contains payments of type T1 and 1, and P2 contains payments of 1 and P2. So this means that if we have atomic decomposition of a money scheme, those both of those machines that represent the components of the decomposition, they are themselves money schemes. And the first money scheme corresponds to payments of this type, and the second money scheme corresponds to payments of this type. We can define sigma 1, the money of B owned in the first component by B is the largest amount of money B can pay with a sequence transactions of this type. And the same in the second component, how much B can pay with transactions of this type. We can show that the sum of those two ownership components is equal to the sum of money B has in the original scheme. So we can also show that total money sigma 1 of the first money scheme and sigma 2 of the second money schemes are invariant, and their sum is equal to the total money in the original scheme. So there is no transfer of value from first component money scheme to the other and vice versa. And this means, for example, for account scheme that it cannot be atomically decomposed such that the first component handles certain accounts and the second component handles another set of accounts, because there is no transfer of value between. You can't pay from account in this system to account in this system. Okay, so more general, we can define unit-wise atomic decomposition as a rule, we have a rule that divides the set of units into two non-intersecting subsets, U1 and U2, so that every payment in the first money scheme acts only on U1 and does not delete, create, or change the parameters of the units in the other set. And every payment in the second money scheme, it acts only on U2 similarly. What we can derive from about unit-wise atomic decomposition, the general result is that if the set of allowed payments contains composition irreducible payments with input complexity 2, the input unit of which are in two different components, then the money scheme is not unit-wise atomically decomposable. And the implications are that a Kant money scheme has no unit-wise atomic decomposition because it implements two-unit swap, which has complexity 2. And the same about UTXO money scheme. It has no unit-wise atomic decompositions because it implements two-unit join. Bill money scheme has unit-wise atomic compositions, as single bill payments have complexity 1 and they can be executed in parallel. So how bill money schemes actually can be unit-wise decomposed? So we can show that bill money scheme enables total unit-wise atomic decomposability, which means that every bill can be maintained by separate transaction validator that produces a single bill ledger or bill ledger of a unit U in the form where S0 of U is the initial state of this bill, and we have completely analogous representation of the ledger. So this ledger is about just one bill. This is the additional information for verifying the bill ledger certificates. Usually it's in the form of a hash chain. Okay, so central bank digital currency, it's about security now. So central bank digital currency is implemented as a permission blockchain. Certifier is under the control of the central bank. Transaction validator and file repository are outsourced to public sector. Okay, and the security model we use in this work is we model transaction validator and file repository as an adversarial entity that may deviate from ledger rules. And we assume that the adversaries are so-called covered adversaries. They are assumed successful only if their malicious behavior remains undetected. The certifier is guaranteed to create a unique block certificate for every block number. So because the certifier is under the control of the central bank. We use bill money scheme where every bill has a bill ledger. At every payment with a bill U, an audit protocol is executed to verify that ledger rules are fulfilled. So as I mentioned, transaction validator is outsourced, so we cannot exclude possible misbehavior. But by using the audit protocol, we try to discover any deviation as fast as possible. So we look at two audit protocols: full audit that guarantees that the ledger rules are followed, and probabilistic audit that guarantees that any deviation will be detected very soon with high probability. So the rules of the bill ledger. Let U be the set of all bills, and initial bill of U, a unit U, is denoted as beta 0 of U. Every block of the bill ledger is either empty or contains a payment. If it's empty, nothing happened with the bill at this block. And payment order is in this form, it contains unique identifier of the bill, the bearer, next bearer, and lambda is reference to the previous payment, and this is the signature of the payer. So lambda should be a cryptographic hash of the identifier of the bill, and the previous payment, in case it's not the first, it was not the first payment, and it is the initial owner here if this was the first payment with the unit. Okay, and so if n prime was the last non-empty block with this bill, and n is the block where the next payment happens, then those intermediate blocks must be empty. The certificate Cn contains a block hash Rn, and there is a function fh, so that if we apply fh to the unit itself, to the block and to the certificate, we obtain this block hash. And it has collision extraction properties, so that if we have two different blocks, there should be B's, not R's, sorry, and we obtain the same result with different block, different certificates, then either we can extract an H collision from the computations, or a bit string X, which is a pre-image of 0 hash. Okay, user side full audit. So every user who has received a bill U with payment, say BU and prime, and later say at block N, the user uses this bill in the next payment, it verifies that these intermediate blocks are indeed empty. Here you see the schematic view of this verification. So the user uses the empty set as argument of the certificate computations, and everything should verify here. And so what is the full audit protocol? Well, how is it exactly going? The user has a bill U paid to her with a payment order PU and prime at block N prime. User's wallet already contains certificate C0 up to Cn prime, the block with the previous payment, and the proof pi, and all they are verified. We assume that. In block N, user creates a new block with a new payment order PUN, with the lambda of which points to the previous payment and sends it to the transaction validator. And user then execute the full audit protocol. It requests certificates Cn prime plus 1 up to Cn, and the proofs from the repository. It verifies the certificate, and it verifies the proofs, assuming that the intermediate blocks are empty for every intermediate block. it extracts the block hashes and it checks whether this fh function indeed results to the block hash. Okay, what does it mean to violate the ledger rules? It means inserting an incorrect block to the ledger. Incorrect block is a block with payment PUI, where PUI does not properly follow the previous non-empty payment. It's not signed by the bearer of this previous payment. And if at the same time, if invalid block is added and the full audit verifies, then we can see that there is a collision or a pre-image of 0. So if ledger rules are violated and the hash function is secure, the verification should not be, the audit should not go through full audit. So the full audit discovers all possible violations. Full audit is costly. So if n is the total number of bills, proof size is k, about k times the binary logarithm of n. And as we need n minus n prime proofs during the audit, total number of bits communicated during this audit may get large if n is much larger than n prime. And we can use probabilistic audit to reduce the communication complexity. And the idea of the probabilistic audit is that we check a d-element subset of those intermediate supposedly empty blocks instead of checking them all. And in this general case, this audit is still inefficient because the detection probability of one single illegal block is about d over, if d is the number of samples, it's about d over the length of the interval, and for high delta, the number of d should be close to n minus n prime, which means that the complexity of the probabilistic audit is similar to the complexity of full audit, and it might be inefficient. How to reduce this complexity is to choose a proper certification scheme of the ledger. And the idea is of using the so-called ledger hash. Ledger hash is a hash value associated to each block, and it's a function of the previous ledger hash and the current block. And it has a property that if there was no payment in this block, then the ledger hash stays the same. And hence, if B, U, and prime is the large non-empty block of U, the current block number and the current block number is n minus 1, then all those hashes should be equal. And we say that those empty blocks are consistent with the payment P, U, and prime. Assume now that if you are using the ledger hash concept and an illegal block is added to the ledger. So we have a payment PUI that incorrectly refers to the previous payment. So maybe not exactly the previous one, but maybe an older one. So we can also say that this payment double spends the bill U. As xi is not equal to x and prime, each of the empty block is either consistent with pu n prime or pui, but it cannot be consistent with both. And the empty blocks consistent with PUN prime, we call them black blocks, and the empty blocks consistent with PUI are called white blocks. And each of the blocks is either black or white. So it's only consistent with one of those payments. We use the gray color here if you don't know which color these blocks are. They are either black or white. And the idea is that if for the next payment block, the audit must show that the empty blocks are black for UN prime. If the payment points to the PUN prime, we should show that all those empty blocks are black. We call PUN as black payment in this case. If these payments refer to PUI, the audit must show that all empty blocks are white blocks, and we call PUN as white payment in this case. And if you randomly choose a block number in this range, the probability that PUJ is consistent with PUI is less or equal than 1/2, or the probability that this block is consistent with PUN prime is less or equal than 1/2. And hence, an audit with one randomly selected block is in at least one of the two cases succeeds with probability not larger than 1/2. Yeah, so the general case is that the adversary has to execute black and white payments, alternating black and white payments. And we assume that bill U is paid to two different users, P and P prime, at block N0 and N1 respectively. Here is N0, here is N1. And at block N2, the user B pays U to another user, and in block N3, the user B prime pays U to another user. And at block N4, the bill is being paid again, etc. And we assume that the adversary can delay payment processing and choose the blocks, the numbers of the blocks N1, N2, N4, and etc., in an appropriate way to hide the inconsistencies. Assume that for any payment, the adversary wants every audit to succeed with probability at least 1/delta, 1 minus delta. For audit at N2, there has to be at least 1 minus epsilon times N0 plus N1 black blocks between N0 and N2, because all blocks have to be shown to be black during the audit, where 1 minus delta is 1 minus epsilon to the power of d. D is the number of samples. And for audit at N3, at the same time, there has to be 1 minus epsilon to multiplied by N1 plus N2 white block. There should be that many white blocks. So what the adversary can do is to delay N3 just to get enough white blocks to be for the audit to get through. And we can show that this formula holds, which means that the required delays between payments must grow exponentially, which is not realistic, clearly, in practice. So using the probabilistic audit, it will reveal any inconsistencies very soon. Conclusions. We showed that the existence of secure and scalable blockchain solutions for CBDC depends on the choice of money scheme. We showed that for the bill money schemes, such solution exists. Central banks can outsource technical operations of payments to the private sector while still having full control over the money. And we showed how client-side audit can discover any potential misbehavior of the operating party. It is not known for similar client-side audit procedures for account or UTXO money schemes, at least to our knowledge. Thank you. All your questions are welcome via email. Thank you for attention.